OK, wow. I mean, thank you, by the way, to JSConf EU for having me here. It's an absolute privilege to be at the last JSConf EU of its time. So can you guys just give it up for JSConf EU? Because like, it's been an absolute... I can't believe it. I cannot believe it. So, you know, biggest JavaScript conference in Europe. I think probably biggest JavaScript conference in the world. Going to be talking about building a JS engine. Yeah, there's like no pressure at all. You know, it'd be completely fine. I should probably introduce myself. So I'm Jason Williams. I'm a senior software engineer at Bloomberg in the UK, in London. Dare I say Europe. And we're still clinging on. We're still clinging on. And basically, I used to also work at the BBC for a few years as well. Some BBC people here. Yeah. Hey. Wow. And I've also been involved in sort of TC39, so I've been working on the promise.allsettled proposal over the past year. And that basically allows you to get the result of all of your promises, regardless of their states, whether they've fulfilled or rejected. And then it's up to you. You have the control then to sort of do what you want with them. On the Rust side, so I've also been involved in Rust as well. I used to be the maintainer of the Sublime Text Rust plugin. I've handed that over since. But then since then, I've moved into sort of like the Rust DevTools team, and they focus on sort of IDE plugins, tooling, and then the Rust language server as well, which is pretty cool. That's basically a single process that handles things like debugging and hinting, and then all the editors can make use of that. So I thought, you know, doing some sort of specifications with JavaScript, really interesting. You know, working a little bit on Rust as well. My two favorite things. How can I marry these two things together? You know, my two languages that I love so much. How can I bring these together? And by the way, biggest JavaScript conference in the world. I know it's a ballsy move coming here and talking about Rust, but I'm just going to go with it. So bear with me. I thought, why not build a JavaScript engine written in Rust? You know, take the sort of fun and easy accessibility of JavaScript, and then power that with Rust, and then see what we can get. It was a bit ambitious. It was quite challenging. I actually started off by looking for a place where I could contribute to this. Nowhere existed. Like, no one actually built one in Rust before, or at least 2 years ago anyway. There was one single project called, I think it was called JS.rs. And the maintainer basically sort of abandoned it, and it was like 6 years old. And I tried to build it, and there was like 650 errors. And it was basically because he made it at a time when Rust wasn't 1.0, and so the syntax had changed and moved on. And it was literally faster to just build one from scratch than it was to try and get this working. So that's exactly what I did. I just thought, let's give it a go. I'm not an expert, by the way, in parsing or writing compilers or any of that. I mean, I even struggle to read CSS in the morning, so I'm not exactly an expert in parsing source code or anything like that. But I thought, let's start somewhere. I also realized it was a bit of a jump. I was doing very small things in Rust, and going from like hello world to full-on JavaScript interpreter was probably a bit of a jump. It just reminded me of the owl picture. I probably should have done something in between, like a to-do MVC or something like that. But I knew I was onto something here, that I had a good language. I knew I had something good to work with. And there were a couple of reasons why I wanted to use Rust to build this engine. One was control. So one of the things that Rust says to you is, we're going to give you all the control you can have, plus all the safety. And so I can utilize a sort of close to the metalness of Rust and do all the things I need to do. And then the compile time checks means that I don't really fall over myself. It was quite fast, so it's built on top of LLVM. And that means that all of the years of the LLVM compiler optimizations that they've done, Rust can sort of tap into that and make use of it. Sometimes you can even get faster code gen than Clang, which produces C. There's some memory safety as well. So Rust has a ownership system, which is quite unique. So basically, if you was passing a value into a function, the function is now the owner of that value. And so there can only ever be one owner to a value. And that means that when Rust wants to get rid of data, it can do so with 100% confidence because nothing else is pointing to that thing. So you don't really have dangling pointers or segfaults or anything like that. And that leads really nicely on into concurrency. I might want to make use of this at some point, especially if I want to implement, say, workers or things like that. Again, because of the ownership model, I won't have to worry too much about multiple threads trying to access the same value, and then won't need to worry about data races. All of that is taken care of at compile time, which means that at runtime, I'm not penalized on performance. So thought, yeah, this is a good start. Let's get going. So I started, about 2 years ago, I made a Git repo. I think it was an engine called Boa. Someone asked me yesterday, why did you call it Boa? I went to Australia in the zoo. I saw a really evil boa in the reptile. I thought, I'm naming my JS engine after that. That is an evil thing. And so I'm going to start with a high-level view here. So the architecture that I'm going to go with for now, there's going to be a few things missing for those of you who are familiar with compilers. But the view that I'm going to start with is taking some source code, and that can be from, say, a network, or in this case, just reading from a file, basically. Taking the source code, bringing it in as a string buffer. So just imagine a big string of JavaScript. And I'm going to use the scanner that I've made to break that down into some various tokens. And these tokens, they're basically like groups of characters that are bunched together to have some sort of semantic meaning. So in this case, we've got function as a token, or foo, or the opening parenthesis here. And we're going to generate a few of those, and we're going to put them into an array, and then we're going to send them on to the parser operation. And the parser is then going to take some of those tokens, and it's going to produce expressions. And these expressions are a little bit different, so expressions can hold other expressions. So for instance, if you've got the opening of a function, then we have what we call a function expression, or function declaration. And then the block inside of that function, we've got some variable declarations. So the variable declarations would be children to that function. And that's generally the idea. So let's just step into that a little bit closer. I'm going to take this line of JS here. So let conf equals JSConf EU. I showed this to someone earlier, and they were like, you should have used const. So sorry, I forgot. Right, but we're going to start with let. So imagine that we're scanning this, so the thing that reads the file has done its job now, and it's going to pass this through. And we're going to start scanning this. So the first thing we're going to be sitting on is the let. And we will produce a token from that. And the token in this case is just our object. And we've got the value, because we want to keep hold of the value. That's quite useful. We want to make some sort of category for the token. In this case, it's a keyword. And the reason I know that's a keyword because I took a look up on the spec, grabbed a list of keywords, and then basically codified against that. And so when I take a string, like let, that's got no sort of quotes at the beginning, I know that it's either going to be an identifier or maybe even a token. And so what I start off by doing is I check against my list of keywords, and I know that this one is a keyword because it's in there. With conf, we do the same thing, except conf doesn't exist sort of as a keyword, so we just assume it's an identifier. But as you can see, we're sort of keeping track of the position. The compiler doesn't really need that per se, but it's good if you're debugging and you can output that there's a problem on this line. Or if there's a token we're not expecting, we can say, there was an issue here, and it's on this column, this line number. Punctuation gets its own category. Again, we want to keep the value, and then where we are, and so on. So here we've got some punctuation, a string, an identifier, and a keyword. And we're going to place this into an array and then pass it on to our parser. This makes it easier to deal with when we're traversing through the source code. And if you just want to look at this in Rust, don't worry too much about understanding the syntax or anything like that. But I make use of Rust pattern matching. So think of like switch case. It's very similar, but it's a little bit more powerful. And the idea is that you can take a character, or anything actually, and then the pattern matching allows you to do some destructuring on that. You can say, is it this or this? You can actually do bindings, which I don't have an example of that here. Or we can just say, is it a digit, or is it alphabetic? In this case, we're on let, so it's alphabetic. So we go into a state of trying to parse an identifier. And then we just take this and put it in a loop. And then we go through each character in our source code and then do the same thing. And for each character we land on, that's a state. So we've got a little bit of a state machine going on. If we want a quote, then we're now in the state of parsing a string. If we want a character, we're in the state of parsing an identifier or keyword, and so on. So I've got a demo. This is something I did earlier. I was going to do it live, but Paul Irish is around, so I just wanted to make sure that he's not going to get interference or anything. But this is a very quick sort of writing conf equals JSConf, and then we're going to output some tokens. It's fairly quick. And then there we go. Very similar to what I showed you earlier. We have keywords, and we have an identifier, and our punctuation, etc. So this is now ready to go. We're done in this area. With parsing, we're going to sort of take that array of tokens, and we're going to try to build a sort of tree structure now. So we're going to start building expressions from these tokens. And the way we do that is very similar to how we were iterating through the tokens as well. So with the characters, we had some pattern matching going on. We're going to do the same thing. This time, though, we're able to pattern match on tokens. So now we can say we're sitting on a token that's representing a keyword or representing an identifier. And if it's a keyword, we can say this is also the keyword that we're currently sitting on. And just a quick side note about pattern matching. It's been so successful in Rust, and it's had a lot of success that there's actually been a proposal in stage 1 to sort of bring pattern matching across into JavaScript. So yeah, keep an eye on that. In this case here, we're sitting on top of an if, and we know at this point now our next token should be an open parenthesis. So I've made a utility function here called expectPunc, and that will expect to have a parenthesis, or it'll basically just error out at that point. We can then parse our condition, so this is between the parentheses, and we can make an expression there. And we can do the same thing with the if body, and that is the expression underneath. We've got next there, and what that does is that checks if the next token is else. Else is pretty optional, as you all know, so we may or may not have an else. If we do, then we will parse that as well. And then what we do after that is we've got sort of 3 expressions, the condition, the body, and then potentially the else, and we add those expressions underneath the if expression, so you can start to see the sort of tree structure that we've got. Again, don't worry about the syntax of this, but this is basically implemented using an enum. And the expressions are what we call variants. Each variant can hold another expression, so you get this sort of recursive structure. And the if variant holds an expression which is a condition, which is another expression that might hold other things. The if body, and we wrap the else in an option, which basically means we may or may not have a value there. And it's basically a very safe way of us checking to say, is there an else? If not, don't error, we just move on, and we get a non-value. The box you can see as well, so these are like the types, and the box is basically saying that these are going to live on the heap. And it will manage that for us. So if you take a look at this visually, I've added a little bit more code now. We just had our sort of letconf equals JSConf for you again. I've added a little bit more around that. And if we start with our function, we get a function declaration expression. And then as we work our way down, we get a letconf. And that basically generates a let declaration expression underneath the function. And there's also a const expression as well. In this case, a const expression is just a literal. So that's basically saying it is a value that we don't need to evaluate. It's already there. And so that is also a child of the let declaration. And the reason for that is because obviously you can declare variables without actually defining what they are. In this case, we're defining it as well. So we go down to our if, and we have our if expression, which holds a operation, a condition, a then, and an else. And as I said earlier, the else was wrapped in an option, and we didn't really use else in this case, so it just returns none. Then we go into our if body, which is the block expression, and we have another let declaration, and then that also has a const expression underneath that as well. And then the last thing is the return, which gives us the return expression. So the source code that you see on the left is basically what would generate the tree we have on the right. Again, another demo. So hopefully we can run this, and then there we go. Yeah. And so there's a lot more going on there, and that's because I could only cover so much on one slide. But there's actually even more expressions. So in this case, there's a block expression at the top, and that represents the global scope. And you've got the function declaration underneath. But you kind of get the idea. So now we're going to try and evaluate the tree that we've generated. And there's a couple of things that we need to do and bear in mind. The idea is that we want to walk through the tree and then make decisions based on which expression we land on. So in this example here, we've got a let declaration expression. And the JavaScript underneath is just an example of what that's generated. And so on the right, we've got the sort of Rust code. And what I decided to do was to represent JavaScript values in an enum. And so we've got all the sort of values that you can have on the right-hand side. Symbol is missing. PRs are welcome. But we've got null, undefined, Boolean, string, number, integer, object, and function. Some people are probably wondering why we have integer if all numbers are 64-bit floating points. If you're doing stuff around bitwise operations, we need to convert them to a number, do the operation on that, and then convert it back into a floating point. So it's kind of used internally. Then we take a value and we wrap it in the GC. So there's a really great GC library that somebody made, and it was super useful. And the reason I needed that is because in JavaScript, you can reference one value for multiple functions. And so if that value goes out of scope, you need to make sure that it stays alive. And so the idea here is I can take a value that I've made, put it in the GC, and that GC will automatically handle not garbage collecting that until nothing else needs it, or at least until it goes out of scope and nothing else can possibly point to it. So Manish, who worked on that, I don't know if he's here this weekend, but he did a really great job on that. And I can just basically add that in. And at the bottom line is me generating that. So I have my value data, which is a string, and I pass my string in, and I now have my value. So this is great. We need to put the value somewhere. So I started off by just using hash maps. So basically, the idea was I had a very sort of naive approach, which was whenever we come across a function, create a hash map. Everything inside that function, I'll just throw in there. This was just to get going. It surprisingly got me pretty far. But as you saw the tree earlier, every time I stepped onto a function declaration, I would generate a hash map, and then I would start using that and set my current environment to be that hash map. And then all I would do after that is every time I came across a let declaration, I would just add the value straight in. Now, obviously, real engines do a lot more than this. But if you just want to get going, it was pretty effective. You can see here, though, that very quickly it starts to fail because we have our B here that's in the same environment as the conf. And the B should probably be removed once that block expression finishes. So I realized I probably do need to have more environments than just the one for function. Took a look at the spec. The specification actually points out 5 of them, and it calls them records. I'm not going to read them out, but you kind of get the idea. And so I then took the environment section of the spec and basically implemented that. It was not easy. It was not easy at all. But basically, what I do now is I created function records, I created block scope records, global scope records, and even module records. And then the idea is that every time I made a new record, I'd add some extra metadata to say what record it is, so I knew where to add the value. And I'd also give it a parent property as well, so that I could point to the record that I made previously, and then you start to have a sort of chain, the scope chain, where we can do our lookups. So if we go back to our tree, the idea was I hit a function declaration, I make a function environment. I have a declaration, I add my value in there. I have a block expression, I make a declarative environment, add my value in there. So far, so good. Return is interesting because the conf is not actually in the current environment that I've just made. And so I have to make use of the parent property to do a lookup. So in this case, I'm trying to find where conf is. I say to my environment, can you give me the value for conf? Doesn't find it. It does a lookup into the function declaration scope and gets it from there. And so this is basically the scope chain that you've probably heard, obviously, people talk about. You can actually put your code into various tools that show you the tree. So there's AST Explorer. I think it's just astexplorer.com or something. But you can put .NET, but you can put your code in there, and you can get a good view of how it would be expressed as an abstract syntax tree. It's good fun. So with all of that, let's give this a try. We've got our function again, very similar to last time. And I'm just going to console log it out. So I implemented console log, which basically just prints the value that it's given. And so there we go. And so we have JSConf EU. And that is our app. Thank you. Thank you. It's pretty fast as well. It's pretty fast. And so, yeah, there we go. We've got it working. To begin with, I got small things working. Then I slowly started adding some other stuff. So I think this week, it can do let and const a bit better. Arrow functions were quite easy to add. And once you get the building blocks there, it becomes easier and easier to add more stuff. A couple of performance opportunities. So one is maybe don't parse everything. Most functions that are declared don't end up even being ran. And so it's not worth parsing every single thing you come across, because that can slow things down. SpiderMonkey and V8, they do what's called lazy parsing, where they will come across a function and may not add it to the syntax tree straight away, but they'll make a note of it and then parse it just before it's ran, so it's all parsed lazily. And they'll do this using a pre-parser, and that will sort of go, and it will check through functions, but not actually add them to the AST. So that's one tip. Don't parse functions that aren't going to be called. And all the JS engines that you use today will already do this. Another opportunity is to make use of the concurrency in Rust, so I can actually break these tasks apart, have them run on separate threads, and then pass data between each other. So we've got a scanner, maybe put that on a thread, and then pass the tokens across into the parser, because the scanner doesn't need those values anymore, and it doesn't need to hold on to them. I can go even further than this. I can go even further than this and have another worker that's reading through the file and then passing characters into the scanner, so the scanner can start running before the whole file is even read. And this is actually something that JavaScript engines do today. It's called script streaming, and the new WebAssembly SpiderMonkey engine does this. And so as the script is downloading, it can start running through it straight away. And V8 also does this as well. So a couple of good things. Implementing more JavaScript, I need to do that. A lot of prototype methods aren't there. JIT compilation, hopefully going to be working with somebody who's got a good JIT package for us called Holy JIT. I like that. I'm going to hopefully come back and do some more stuff on the event loop and then talk about that. I've had to leave that out today. And then some more tests around that, and maybe utilizing test 262. So that's it. I've done it. I've brought JavaScript to the Rust ecosystem. People in the Rust world can make use of it. If they want to tokenize, they can do that. It's quite modular. If they want to have a parser in the Rust world, they can do it. They can use it. They have some JavaScript. But then I thought, have I married my love of these two things together? I've brought JS into the world of Rust. Can I bring this piece of Rust into the world of JavaScript? Yes. Yes, I can. There's WebAssembly. I can bring this whole thing into the browser. I know. The Rust team and the WebAssembly working group have been working together for quite a while now to make WASM really awesome, especially via Rust. They've been working on some great tooling over the past few years, and why not take advantage of that? One of those tools was WASM BindGen, and I thought, do you know what? Let's take that and use it with Boa. And then bring that into the browser and have people running JS, JavaScript inception. And the way that that works is actually pretty easy. So you take WebAssembly, bring it onto a place where you want to expose, and you can expose that as an ES6 module. So something like this, basically. I've got a function called evaluate. You pass it a string, it runs, you get a string back. I thought, let's add WASM BindGen to that, build my package, it will generate WebAssembly, and I can use that. There's some advantages to this. It'll be quite fast. It's already compiled, so when the browser pulls it in, it can just run it straight away. Because it's compiled, it's more compact, so you've got a faster download because you're downloading less code. There's still the safety aspect there as well, because it still follows the same rules, like same origin and browser limitations, so you don't get this black box that's making requests where it shouldn't be. And I can expose it to JavaScript. I don't need to rewrite everything. I can just expose this one thing and use it as though it's just a JS module. Even here, looks like a JavaScript import. It's actually Rust I'm importing there. It's not JS. I can pass it a string, and I can run it. That's the WASM bindgen attribute. You put that on the top of any function that you want to expose into the JS world, and it will actually build your package into a WASM file, and then you can import it. A little bit like this. Let's take a look. Highlight there. We're going to build it. I'm doing yarn serve because there's a WebAssembly plugin. That's going to build that out. Take a look on the left. It's going to generate a package folder. It's pretty quick. I can make changes to Rust code, and that will run, and the browser will reload. It's like I'm writing JavaScript, basically. And so now we have a Boa bindgen WASM file, and you can import that into JavaScript. So, final demo. We're going to write some JS. We're going to pass it into WASM. We're going to scan it, parse it, evaluate it. And then we're going to bring that back into JavaScript, and then we'll basically print the value out. I'm going to try and do something a little bit challenging. Over time, it will get more and more challenging, but this is the most I can do right now. Hopefully, we get, we can return hello. We can do plus JSConf. Oh, not WU, EU. Get a second function, and then we can run var. Are you ready? Oh, come on. Wow. That's what keeps me up. You know, this is why I'm in the industry. This is why a lot of us are here, right? That is Rust running there. There's no like secret thing going on. There's no network request. That's Rust running in the browser, executing that JS, scanning it, parsing it, evaluating it, giving it back, and the JavaScript is still there as well. They work hand in hand. So the takeaway is you can take the performance-sensitive parts of your application, build them in something like Rust or C in WebAssembly, and you only need to change those bits. You don't need to change the whole application. But the next time you're thinking of building a JS parser like this one or a game engine, it was super easy, and it's worth doing. It's definitely worth thinking about. You can actually play with the demo as well. It is on that GitHub repo. You can actually go there and play with it live. It's not perfect. And also, there's the WASM book. And I think some people here this weekend will be talking about WebAssembly as well. So hit me up. Thank you very much. I'm super pleased with that. Thank you.